Okay, in this video we shall see the CE amplifier working using Log Discovery Kit 2. This is a circuit we are looking at. So this is a CE amplifier having a potential divider biasing that is provided by R1, R2 and the supply voltage VCC. This is the input voltage, coupling capacitor, the output is taken at the collector. This is how that circuit is connected. So as you can see now, this is a compact way of connecting the circuit. So we are using the pins that are provided along with the kit. So you can see this vertical line. So one is in order to systematically use the AD kit. So let us use this vertical line. Okay, here we are connected to the last vertical line, the ground, and to the next to it is the VCC. Please also connect the black wire for ground and the red wire for the VCC. So whichever resistors, capacitors are in whatever circuit that is to be connected to VCC. So you can see now there is a resistor connected to VCC and there is one more resistor connected to VCC. You can see here. So from your circuit diagram, if you just look back the circuit diagram and see, so we have these two resistors connected to VCC, R1 and RC, and there are so many points which are connected to ground. So that is this resistor, this second resistor and a capacitor. If you just go to this, and you can see there are two resistors. This is 2.2k, which is RC. This is the another resistor, which is this is, you can see, so this is actually the ground connection, the last one. This is 6.8k. So this is actually connected to the VCC. This is 2.2k and this is 47k. So this is a way how you can effectively utilize this power supply lines to effectively connect it. Now this is a transistor, and we're going to use this for the ground. This, sorry, first one is for VCC, second is for ground. The third one will be used for waveform generation, where you can give the input voltage. So this is that W1 will be connected here, and this is the one more dummy point which is connected to this, so that you can effectively see the input voltage. And this blue one is the channel 2, where you can see the output. So this is actually connected to the collector point. So now you can see this capacitor, which is a coupling capacitor, is connecting to this yellow wire where the input is given, and it is now coupled to the base. So this is the base terminal, and we have this as the collector, this is the emitter. We have this capacitor connected within the center tap of the this is the center tap of your uh, pot. So that is connected to one end of the capacitor, the other end is grounded. One more end of the pot is connected to ground here, the other end is connected to the emitter. You can see this is emitter is connected to this is exactly the way how the circuit diagram looks in your circuit diagram. So this is a pot. So one end is connected to capacitor, the other end is connected to emitter, other end is connected to ground. So this way you can effectively connect the components very compact way. We shall see in closed loop, okay, how does these elements are connected. So this is a very compact connection. You can see this is grounded, this is going to emitter, and this is your VCC. This is 47k, this is 2.2k, it's again connected to VCC. This, you can say, this is 6.8k connected to ground. This is your ground point, this is your VCC. This is the input voltage which will be applied, which is then connected to the coupling capacitor, will be going to the base. And this is collector, this collector is connected to the RC, and RC is in turn connected to VCC. This is output point where you are connected, it's connected to the collector. You can see the output over here. So let us see how does these pins are connected to your AD kit. Now this is how this AD kit wires will be connected. So this is your VCC. The wire from the AD kit will be connected onto that male connector. So this is VCC ground, this is the waveform 1. So this is channel 1, where you can see the input voltage. The channel 2 will be connected to output. So this blue one, please stick to that what color code. Whenever there's a VCC, please connect a red wire. Wherever it's a ground, you connect the black. Wherever it is output, please have the yellow wire. For the input, you just connect the LO one, because LO corresponds to W1 in your AD kit, so it will be easy for you to identify the circuits. Okay, after making the circuit diagram, so let us verify the voltage at the collector point. At the collector point, in this typical design, we are looking at a typical design having these specifications with a magnitude of the gain as 50, IC is equal to 1 milliampere, this is VCC, assuming beta as so and so. So we are ending with the standard values of resistors as this much. So at the collector point, so we are expecting an voltage of at this point. So since the RC is 2.2k, this is 5 volt. If 1 milliampere current is flowing, we are expecting a voltage of 2.8 volts at this point. So let us actually conduct the experiment and try to find out what is the voltage at the collector, whether it is 2.8 or not. If it is 2.8, we'll connect the input voltage. Otherwise, we'll just make sure that the voltage over here is almost close to 2.8 volts, so that 1 milliampere current flows to that. So now let us do this first connection. So let us ensure that the biasing of the circuit is proper not. Okay, this circuit is actually made in the AD kit. Okay, using the AD kit, let me apply this VCC and see the voltage at this point. So let me just do that simulation. One second. One second. Now, as per the design values for the assumed assumptions, so R1 is connected as 47k and R2 is connected to 6.8k. I'm just looking at the voltage at this point, at the collector point. So it was supposed to be 2.8 volts if 1 milliampere current is flowing, but we are having a current of we are having a voltage at the collector as 4.62 volts, which means that the current flowing through the resistor RC is far less than 1 milliampere. This was supposed to be 2.8 volts. Now what we need to, so this indicates that the current flowing through the resistor RC is less than 1 milliampere. So we need to increase the current. So in order to increase the current, one of the possible ways, you have to increase your VBE. The VBE can be increased using Vx. So Vx can be increased either by reducing R1 or by increasing R2. So let me increase the value of R2 from 6.8k to some larger value. So what I'll do is I'll simply connect 3.3k resistor in series with this 6.8k, which is in at present now. So which will actually increase R2. So naturally this Vx will increase, which will increase VBE. So naturally the IC has to increase. So let me do that connection now. Now the circuit has been modified with the value of R2 as 6.8k plus 3.3k resistor. Actually, I have connected one 3.3k resistor along with that 6.8k resistor. Now, which has increased the value of Vx over here, which will going to increase VB. So naturally, the IC will increase. When IC increases, we're going to have a reduced voltage at the collector. Now we can see the voltage at the collector is around 2.92 volts. So now we can say approximately to 1 milliampere current is flowing through RC. Now at this stage, so we have a proper DC conditions with a current of IC, which is nothing but now 5 minus almost 2.9 divided by 2.2 k resistor. It's almost equal to 1 milliampere is flowing through the transistor. So let us apply the AC signal and then we shall see the amplification. As it is already seen in the previous slides that okay, we have connected the circuit from W1. So this is your W1. So this is W1 connected to the input, and the output is taken here. This is the input waveform. So what I'll do is I'll give the waveform. So let me select the waveform generation. So let me select first waveform. Let me keep the frequencies around 20 kilohertz, so which is in the mid-band range. So let me make the frequency as around 20 kilohertz. So I'll make it around 20 kilohertz and let the frequency of the signal be in terms of some millivolts. So let me keep the frequency around 0.5 0.01 volt. Now this is the amplitude that I applied. Now let me run this. There is an input voltage applied with a frequency of 20 kilohertz. So let me again go for the scope and observe the waveform. Now we can see the waveform is coming, and let me just change this time base because the frequency is in terms of kilohertz, so I have to go for a reduced scale. So let me make it something like, now you can see, now this is, you're seeing a waveform now. So let me just make it somewhere 0.02. Now we are seeing the waveform, and let me just increase the amplitude here. So let me reduce the range of input voltage. Input voltage, let it be, because the input voltage range is very less. Let me make it, now it is 0.05. Let me make it 0.01. Now this is the input voltage that is applied, and let me change the volts per division for this as around 1 volt. Now you can see this is the output voltage, the input voltage is this. Now let us actually measure the peak to peak of input and the output. So let me just measure the parameters corresponding to the peak to peak input voltage and the output voltage. This is done, and let me, so we have the input voltage peak to peak and output voltage peak to peak. So if we can actually note this C1 happens to be the input, which is 28 millivolt, whereas the output is 375 millivolts. So we can actually find what is the gain of this amplifier. So let me just calculate the gain and then come back to you. Now for this particular case, the gain of the amplifier is coming as like 13.39, so which is less than what we expected. So what we are supposed to do now is, under such condition where the gain is less, it is purely because we are supposed to change the value of RE, because we know that as the value of this pot, suppose if the center tap of your pot is there on the top, you're going to have the maximum gain. If it is there at the bottom, we're going to have the least gain. So let me change the position of this pot so that this RE dash changes, because as this RE dash changes, we know that the gain of your amplifier will also change. So which we already studied in the equations, that okay, as your RE dash changes, the gain will going to be changing. So let me change this value of RE dash to a very small value. You can see this gain will going to increase. Let me do that. Now we can see I have slightly changed the RE dash value. Now the, you can see now the peak to peak is now almost 1.41 volts, whereas the input peak to peak are almost just only 40 millivolts. You can actually find the gain of this. Now it is 1419 divided by 40. Now the gain is coming out to be 35, whereas in the previous case the gain was around 13. So let me again change the value of RE dash. Now the value of RE dash is again changed. Now the value of RE dash is so low that the gain is now almost close to 47. So let me see the frequency response of this by doing that network analyzer. Now we should see the frequency response of this amplifier. So let us add one network analyzer. I'm just adding the network analyzer. So since now it is the gain versus the frequency, now network analyzer, let me run this. I can see while selecting this, let the amplitude of the input voltage be in terms of 100 millivolt. Let the start frequency be 20 hertz. The end frequency is 5 megahertz. Now the frequency is changing from 100 hertz to 5 megahertz in the scale of, now it's a logarithmic scale. Now we can see the gain is increasing. The gain is increasing now. It becomes fairly constant. So this is your midband gain. So when it is 20 kilohertz, this was the gain what we are getting. So which was around 30. This is in terms of dBs. Now you can see output is reducing. So this is exactly in line with your what you expected. If you can just go back and see the frequency response of your circuit, so this is what you are expected. So we are supposed to have a line which is come down, so on either side, so we are actually getting the expected graph.